Before July 1, 2025, astronomers thought they understood interstellar visitors. We had two previous examples. We had clear theoretical models, and we had instruments capable of solving any mystery the cosmos could deliver. Then 3 Atlas arrived, and our confidence evaporated like ice in sunlight. The more we study this object, the less sense it makes. It produces carbon dioxide at rates that should be impossible for its size. It maintains gas clouds that extend farther than Earth's orbit around the Sunday. It shows chemical signatures that don't match any formation environment we can imagine. Each new observation forces us to question assumptions we thought were settled science. The world's most powerful telescopes are essentially admitting defeat. Defeat against a chunk of rock and ice barely larger than a small city. What does it mean when our best science fails to explain something as simple as a comet? Join us as we explore why this visitor might represent the most important discovery of our lifetime. Or perhaps it's proof that the universe still holds secrets we're not ready to understand. Why 3 Atlas just doesn't make sense. On July 1, 2025, at precisely 14 hours 37 minutes, universal time, something changed. It changed the trajectory of our understanding of the cosmos. Not in some distant galaxy, not in the theoretical realm of academic papers, but right here in our own solar system. The Atlas survey station in Chile captured something that shouldn't exist. It was a routine automated telescope scanning the skies for potentially hazardous asteroids. The object appeared as nothing more than a faint smudge against the starfield. It was a moving dot at 4.5 astronomical units from our Sunday, but within hours the orbital calculations revealed a truth that sent ripples through the astronomical community. This visitor was traveling on a hyperbolic trajectory. Its eccentricity was far beyond 1. In the language of celestial mechanics, this means it's unbound. It will never return to our solar system ever. They designated it C divided by 2025 N1 Atlas. But to those who study the wanderers between the stars, it became known simply as 3 Atlas, the third confirmed interstellar object to grace our cosmic neighborhood. The speed alone should have been our first clue, a clue that we were dealing with something extraordinary. 130,000 miles per hour, 209,000 kilometers per hour. That's not just fast by earthly standards. That's the fastest solar system visitor we've ever recorded. To put this in perspective, imagine a bullet traveling at typical velocity. Then multiply that speed by 170. That's 3 Atlas screaming through space with the momentum of an entirely different star system. But speed, as we would soon discover, was only the beginning of its mysteries. Within days of discovery, the Gemini North Telescope in Hawaii turned its mirror toward this interloper. What it revealed defied our expectations of what an interstellar rock should look like. There, surrounding the invisible nucleus, was a fuzzy compact coma, a cloud of dust and gas being actively released by solar heating. This wasn't some cold, dead fragment of interstellar debris. This thing was a live, breathing vapor into space as our sun's energy awakened dormant ices that had slumbered for millions of years in the cold between the stars. The implications struck the scientific community like a meteor. Here was an object that had traveled the galactic wilderness. It survived radiation that would sterilize any earthly organism. It endured temperatures just a few degrees above absolute zero. Yet the moment our sun's warmth touched it, it began to sublimate. It began to transform directly from ice to gas, creating a ghostly atmosphere in the vacuum of space. But perhaps most unsettling was what this activity revealed about its orbital path. 3 Atlas wasn't just passing through our solar system. It was threading the needle between planetary orbits with surgical precision. Its closest approach to Earth would be 1.8 astronomical units. That is roughly 270 million kilometers. Safe, yes. But the geometry was almost too convenient, too perfect for observation. NASA immediately marshaled its most powerful instruments: the Hubble Space Telescope, the James Webb Space Telescope, the Swift Observatory, and the Transiting Exoplanet Survey satellite. The European Space Agency coordinated global tracking efforts. This wasn't just another comet to catalogue. This was a messenger from another star system. It carried chemical signatures that could reveal the conditions in an alien planetary nursery. Yet, even as the world's most advanced telescopes turned their attention to this visitor, a pattern emerged. Every observation seemed to raise more questions than it answered. The object's behavior matched no existing model of interstellar debris. Its chemistry defied conventional wisdom about comet composition, and its very presence in our solar system suggested formation conditions unlike anything local. The irony wasn't lost on the researchers studying it. Here was an object from light years away, farther than human imagination could truly grasp. Yet it would spend the next several months within the familiar confines of our solar system, a cosmic visitor staying just long enough for us to study it, but moving so fast that every observation window was precious and fleeting. As July turned to August, the first detailed images began streaming back, and one thing became crystal clear: Free Atlas wasn't going to give up its secrets easily. If anything, the more we learned about it, the more mysterious it became. The stage was set for a chase against time itself, a race to understand this enigmatic wanderer before it disappeared forever into the cosmic dark. The path through our neighborhood. Picture the solar system as a vast clockwork. Planetary orbits mark predictable paths through space and time. Now imagine a bullet fired from another galaxy, streaking through this cosmic machinery at impossible speed, threading between the gears with mathematical precision. That bullet is 3 Atlas, and its trajectory through our neighborhood tells a story of cosmic timing, a story that borders on the theatrical. The visitor's itinerary reads like a carefully planned tour of the inner solar system, yet it was written in the stars long before Earth existed. Perihelion, its closest point to our Sun, would occur on October 29th, not at the comfortable distance of most comets, but a scorching passage between the orbits of Earth and Mars, roughly 130 million miles from our star, close enough for the Sun's energy to boil away ancient ices, yet far enough to avoid complete destruction. But here's where the cosmic choreography becomes almost cruel. As 3 Atlas makes its closest approach to the Sun, Earth will be on the opposite side. For nearly 2 months, from late September through early November, our visitor will be lost. It will be lost in the Sun's glare, invisible to every telescope on or orbiting Earth. It's as if the universe conspired to hide the most important moments of this encounter. The observational window tells a tale of astronomical frustration. Scientists have roughly 3 months to gather data before 3 Atlas vanishes. Then, perhaps 6 weeks after it emerges in December, it will become too faint. It's a deadline that would make any investigative journalist nervous. Except these journalists are studying something that won't be back for another visit ever. Yet the trajectory offers tantalizing opportunities. On October 3rd, 2025, 3 Atlas will streak past Mars. It will pass at a distance of just 29 million kilometers. That's closer than Mars' own moons come to the planet. For the fleet of robotic explorers orbiting the red planet, this is an unprecedented chance. A chance to photograph an interstellar visitor from an alien vantage point. The geometry is everything in astronomy. And this geometry is both a gift and a curse. When 3 Atlas reappears in Earth's skies in early December, it will grace the pre-dawn hours. It will be in the constellation Virgo, climbing toward Leo as the weeks progress. But by then, it will be racing away from the Sun at over 150,000 miles per hour. It will grow fainter each night as it returns to the cosmic deep. For amateur astronomers hoping to glimpse this visitor, the news isn't encouraging. At its brightest, 3 Atlas will barely reach magnitude 11 or 12. it will be visible only through telescopes. It will appear as nothing more than a faint, fuzzy star among millions of others. There will be no naked eye spectacle, no brilliant tail stretching across the sky like Comet Hale-Bopp or Neowise. This visitor prefers to keep a low profile. The orbital mechanics reveal another layer of the mystery. 3 Atlas isn't just moving fast, it's moving wrong. Its hyperbolic orbit suggests an origin velocity of roughly 25 kilometers per second. That's fast enough to escape not just our solar system, but potentially the gravitational embrace of our entire galactic neighborhood. This isn't some recently ejected debris from a nearby star. This is something that has been wandering the galaxy for a very, very long time. As spring turns to summer, in 2026, 3 Atlas will make another passage. This time, it will be near Jupiter in March. This distant encounter has already sparked proposals for redirecting NASA's Juno spacecraft. The audacious idea would require precise orbital mechanics and perfect timing. It would transform a mission designed to study Jupiter into humanity's first close encounter with an interstellar visitor. But perhaps the most humbling aspect of this celestial schedule is what it reveals. It reveals our own cosmic perspective. Here we are tracking an object with instruments worth billions of dollars. We are coordinating observations across multiple space agencies, and we are marshalling the finest minds in planetary science, all to study something that will spend less than 2 years in our vicinity. Then it will disappear forever into the galactic night. The path of 3 Atlas through our solar system isn't just a trajectory. It's a timeline of opportunity and limitation, of windows opening and closing according to the ancient laws of orbital mechanics. And every day that passes brings us closer to our final chance to solve the mystery. First, look's what Hubble sees. When the Hubble Space Telescope first turned its unblinking eye toward 3 Atlas, the universe offered us a paradox wrapped in starlight. The image that emerged from Hubble's sensors was both familiar and utterly alien. A teardrop-shaped cocoon of dust and gas glowing softly against the infinite black, yet possessing a geometry that no textbook had prepared us for. The technical details read like poetry written in the language of physics. The nucleus, the solid heart of this interstellar wanderer, remained stubbornly unresolved. It appeared as nothing more than a bright point source buried within its own shroud. But Hubble's exquisite optics allowed scientists to place an upper limit on its size. No more than 3.5 miles across, roughly 5.6 kilometers in diameter. To put this in perspective, that's smaller than most earthly cities. Yet this tiny fragment was generating a coma that stretched thousands of miles. But here's where the familiar becomes strange. Hubble tracked the comet against the background stars. It kept 3 Atlas perfectly centered in its field of view. The result, the stars themselves, appear as bright streaks across the image. This creates an ethereal backdrop that makes the comet look like it's flying through a tunnel of light. It's a photographic technique that transforms scientific documentation into accidental art. It reveals the relative motion that separates this visitor from everything else. The coma itself tells a story of thermodynamics on an interstellar stage. As 3 Atlas approached the Sun, the nucleus began shedding material. The dust particles liberated from their icy matrix formed a roughly spherical cloud, but with a distinct elongation pointing away from the Sun's path. This wasn't random. This was physics in action. Solar radiation pressure and gravitational forces were sculpting the coma. Yet something seemed off about the tail. In most comets, the anti-solar tail is prominent and easily visible. In 3 Atlas, this feature was puzzlingly subtle, almost hidden. Initial Hubble analyses suggested its presence, but couldn't confirm it with confidence. The geometry seemed wrong, as if we were viewing the tail from a compressed angle. This ambiguity would persist until late August. That's when the Gemini South telescope captured deep images that finally revealed the tail. There it was, a faint but definite anti-solar tail extending away from the Sunday. The astronomer's telegram made it official. 3 Atlas possessed the tail that theory demanded, but it was playing by its own rules of visibility. The dust loss rates provided another puzzle piece. Hubble's measurements showed that 3 Atlas was shedding material at comparable rates comparable to solar system comets at similar distances. This might seem reassuring evidence of normal predictable behavior, except for one crucial detail. This object had been wandering interstellar space for epochs. It had been exposed to cosmic radiation that should have altered its surface. Yet here it was behaving like a fresh comet on its first passage. The resolution of Hubble's images revealed another layer of the mystery. While the telescope could constrain the nucleus size, it couldn't resolve any surface features. The nucleus remained a point source. Its secrets were locked behind the glowing veil of its own emissions. We were studying this visitor through the fog of its own making, like trying to examine a lighthouse bulb while standing in its beam. Perhaps most intriguingly, Hubble's observations hinted at structure within the coma. The dust distribution wasn't perfectly smooth. There were subtle variations in brightness and density. This suggested active regions on the nucleus surface. Somewhere beneath that shroud, specific locations were venting material into space. But without higher resolution, those patterns remained as cryptic as ancient hieroglyphs. The photometry revealed another surprise. 3 Atlas was brighter than expected for an object of its estimated size. This suggested either a larger nucleus or a surface with unusually high reflectivity. Both possibilities raised questions about its composition and origin. Dark carbon-rich materials would produce a faint object. Bright icy surfaces would create the luminosity Hubble observed. But the spectrum of possibilities left too much room for speculation. As August progressed, Hubble's observations captured the dynamic evolution of the coma. The dust cloud was growing, expanding as solar heating intensified. Yet the nucleus remained unresolved, a cosmic tease. The images would soon be joined by data from other instruments, each adding pieces to a puzzle that seemed to grow more complex. But Hubble had established the visual baseline. This was no ordinary chunk of interstellar debris. This was something that demanded explanation. In the gentle darkness of space, 3 Atlas continued its ancient journey. Now illuminated by our sun's light and scrutinized by humanity's finest instruments. Yet for all our technological prowess, the visitor remained essentially unknowable. The chemistry surprise. The universe has a way of keeping astronomers humble, and 3 Atlas was about to deliver a masterclass in cosmic humility. When the James Webb Space Telescope first analyzed the visitor's spectral signature, the results shattered every expectation. The numbers told a story that made no sense. A carbon dioxide to water ratio of 8 to 1. 8 to 1. To appreciate how extraordinary this measurement is, consider that most comets show the opposite pattern. Water dominates their chemistry by factors of 10 to 100. Even the most water-poor comets rarely exceed ratios of 2 to 1. Yet here was 3 Atlas flaunting a chemical signature so extreme it placed it in a category of 1. But Webb's discovery was only the opening act. Between August 8th and 12th, the SphereX mission turned its attention to this interstellar oddity, and it uncovered something that defied every model of comet behavior. The carbon dioxide emission wasn't confined to a small region around the nucleus. Instead, it extended outward for at least 348,000 kilometers. This created the largest carbon dioxide coma ever mapped around any comet. Imagine the entire Earth-Moon system. Then stretch that distance another 50%. That's the scale of 3 Atlas carbon dioxide envelope, a ghostly sphere of gas large enough to swallow multiple planetary orbits. The sheer size of this emission region suggested processes on scales that challenged our understanding. The spectroscopic data painted a picture of chemical extremes, while Webb detected robust carbon dioxide emission lines the water signature was strangely muted. It was so faint that some observers questioned whether 3 Atlas contained significant water ice at all. This stood in stark contrast to earlier reports from the Swift Observatory. Swift had detected hydroxyl radicals that typically indicate water. Somewhere in the translation from ice to gas, the water story was getting lost. Spherex added another twist to the chemical narrative. Its wide-field spectral mapping revealed absorption features consistent with water ice, so the ice was there locked in solid form. But something was preventing it from sublimating efficiently into the gas phase. The surface was holding secrets that the spectrum could only hint at. The contrast with previous interstellar visitors was striking. 2 Borisov, discovered in 2019, had shown elevated carbon monoxide. That chemical signature suggested formation in a cold outer disk environment. But carbon dioxide tells a different story. It forms at intermediate temperatures in regions where water would be liquid or vapor. But carbon dioxide could still freeze out of the gas phase. The implications rippled through theories of planetary formation. If 3 Atlas formed near a carbon dioxide snowline, it might represent material from a new zone, a zone analogous to the asteroid belt in our own solar system. Such environments might be common around other stars. But WED never sampled material from one before. The extended carbon dioxide cloud raised even more profound questions. How does a nucleus only a few kilometers across generate such an enormous emission region? The physics demanded either an incredibly active surface, far more active than anything we'd seen, or a fundamentally different mechanism for releasing gas into space. Some researchers proposed that 3 Atlas might be fragmenting, releasing carbon dioxide-rich chunks that continue to sublimate. Others suggested that the extended emission might result from solar-wind interactions. Both explanations stretched the boundaries of conventional comet science. The timing of these discoveries couldn't have been more dramatic. Just as 3 Atlas was approaching the optimal viewing window, its chemistry was proving unique. We were watching a unique chemical laboratory in motion, powered by our sun but carrying the frozen history of an alien planetary system. Yet the carbon dioxide dominance also carried a sobering implication. If this was typical of interstellar material, then our models of planetary formation might be missing pieces. The chemical diversity of 3 Atlas, plus the signatures of Oumuamua and Borisov, suggested something. The galaxy harbors a population of ejected debris far more varied than our theories predicted. As August progressed, astronomers found themselves in possession of data that was both unprecedented and insufficient. The chemistry of 3 Atlas was clearly extraordinary, but whether it represented a new class of object or an extreme example of known physics was unclear. The universe, it seemed, was determined to keep us guessing until the very last moment. What we still don't know. 3 months after discovery, we find ourselves in a peculiar position. We know too little about too much. Each observation has revealed new facets of this interstellar enigma. Yet the fundamental questions that matter most remain tantalizingly unanswered. The nuclear size exemplifies our predicament perfectly. Hubble's imaging constrains the diameter to a range so broad it's almost meaningless. It encompasses everything from a large building to a small city. This isn't a failure of instrumentation. It's the inevitable consequence of studying an unresolved object shrouded in its own atmosphere. The nucleus could be a compact bright sphere or an elongated dark chunk. Without direct resolution, we're essentially guessing. The rotation state remains equally mysterious. Most small bodies spin with periods measurable in hours. Their changing cross-sections create detectable brightness variations. But 3 Atlas has proven frustratingly stable in its apparent brightness. It shows none of the periodic variations that would reveal its spin rate. Either it's rotating very slowly, or its surface features are remarkably uniform. Each possibility carries different implications for its origin and structure. The water question has evolved into something approaching scientific drama. Early observations by the Swift Observatory detected hydroxyl radicals. This is typically a reliable indicator of water vapor, but SPHERIC's subsequent mapping found the water signal surprisingly weak. Either the water is there but hidden, or our understanding of hydroxyl production needs revision. The tail morphology adds another layer of uncertainty. The Gemini South detection of an anti-solar tail finally confirmed what theory demanded. But why did it take months to clearly identify this feature? The tail's subtlety suggests either unusually large dust grains or a unique viewing geometry. Both explanations raise questions about 3 Atlas' fundamental nature. Activity patterns present perhaps the most intriguing unknown. The Hubble images show a sun-facing elongation of the coma, material apparently flowing toward our star rather than away from it. This counterintuitive geometry initially puzzled observers. The apparent sunward drift might be an optical illusion, or it might indicate something genuinely unusual about how this visitor releases material. The composition mysteries extend beyond the carbon dioxide dominance. What about organic compounds, sulfur-bearing species, noble gases? Each trace constituent could provide clues about its formation, temperature, and radiation exposure. But detecting these species requires observation time that's rapidly running out. Perhaps most frustrating is our inability to study 3 Atlas around perihelion. The solar conjunction blackout means we'll miss the climactic moment. We'll only see the aftermath, like arriving at a theater after the final curtain call. The speed of 3 Atlas compounds every observational challenge. Ground-based telescopes must track at rates that push their systems to the limits. Space-based instruments face scheduling constraints as the target moves rapidly, and the ever-increasing distance means that every week of delay degrades the signal. The kinematics tell their own story of uncertainty. While the interstellar origin is confirmed, tracing 3 Atlas back to its birthplace is difficult. It requires precise knowledge of its trajectory, knowledge that's limited by our brief observational window. The current best estimate suggests an origin in the galaxy's thick disk population, among stars that formed when the universe was perhaps half its current age. But that's educated speculation based on incomplete data. Even the basic question of what drives 3 Atlas activity remains open. Is it sublimating ices like a normal comet? Is it fragmenting under thermal stress? Could it be electrically charged? The extended carbon dioxide coma suggests activity on scales that simple models struggle to explain. As we approach the solar conjunction deadline, the mounting uncertainties create a peculiar tension. We know enough about 3 Atlas to recognize its extraordinary nature, but not enough to understand what makes it extraordinary. The December reappearance will offer one final chance to solve the mystery. The universe, it seems, is fond of visitors who arrive with more questions than answers. What counts as interstellar? The cosmos doesn't issue passports. But if it did, 3 Atlas would carry credentials from another star system. Understanding what makes an object truly interstellar requires diving into orbital mechanics, a language where eccentricity values and hyperbolic trajectories tell stories of cosmic wandering. In the precise terminology of celestial mechanics, any object with an orbital eccentricity greater than 1 is unbound. It's following what mathematicians call a hyperbolic trajectory, a path that opens into infinity rather than closing into an ellipse. 3 Atlas has an eccentricity of approximately 1.7, meaning it's not just unbound, it's traveling so fast that even Jupiter can barely deflect it. But eccentricity alone doesn't tell the complete story. The truly diagnostic measurement is called v infinity, the velocity an object would have relative to the Sun if it were infinitely far away. For objects born in our solar system, this velocity is essentially zero. They're gravitationally bound and will eventually return. 3 Atlas has a v-infinity of roughly 25 kilometers per second. This confirms beyond doubt that it originated elsewhere. To appreciate this velocity, consider that Earth orbits the Sun at about 30 kilometers per second. 3 Atlas is moving nearly as fast relative to the solar system as our entire planet. That's the momentum of another world entirely. The kinetic signature of a different formation environment. The discovery process itself reveals how rare these interstellar visitors truly are. The Atlas survey system consists of 4 robotic telescopes designed to scan the sky. In nearly a decade of operation, Atlas has found exactly 1 confirmed interstellar visitor. The statistics are sobering. Interstellar objects are perhaps 1,000,000 times rarer than typical near-Earth asteroids. This rarity isn't because interstellar space is empty, quite the opposite. Theoretical models suggest our galactic neighborhood should contain thousands of interstellar rocks. The problem is detection. These objects are faint fast and follow trajectories that carry them through our system briefly. By the time we spot them, they're often already racing toward the exit. The technological revolution in wide-field surveys has finally given us the tools to find them. Pan-STARRS found Oumuamua in 2017. The Catalina Sky Survey discovered 2 Borisov in 2019. Now Atlas has delivered 3 Atlas. Each discovery required automated systems capable of processing thousands of images per night. The confirmation process follows a rigid protocol. Initial detection triggers rapid follow-up observations to establish orbital elements. Observatories worldwide contribute positional measurements that constrain the trajectory. Orbital mechanics software calculates the best fit orbit. Only when multiple independent analyses confirm hyperbolic motion does an object earn the designation. The naming conventions reflect this careful verification process. The I designation for interstellar comes only after thorough vetting. 1 for Oumuamua, 2 for Borisov, 3 for Atlas. Each number represents not just a discovery, but a confirmed sample from the vast population of debris. Yet, these 3 confirmed visitors hint at a much larger population waiting to be discovered. The Rubin Observatory will begin operations in 2025. Its survey capability dwarfs all current systems combined. Theoretical estimates suggest Rubin might find anywhere from 1 to 70 interstellar visitors per year. This would transform these rare cosmic accidents into routine scientific opportunities. The physics of interstellar designation carries profound implications. These objects are time capsules from other star systems. They preserve chemical and isotopic signatures from planetary formation environments we can never visit. Each visitor is a laboratory sample delivered to our doorstep. The hyperbolic trajectories also mean we get only 1 chance to study each visitor. Unlike periodic comets, interstellar objects are fundamentally disposable encounters. The data we gather represents the only information we'll ever have about these particular samples. As 3 Atlas continues its hyperbolic journey, its interstellar credentials are beyond question. The mystery isn't whether it comes from another star system. The orbital mechanics prove that conclusively. The mystery is what kind of star system could produce such an unusual wanderer, and what its strange chemistry reveals about planetary formation in different environments. 3 visitors, 3 personalities. The universe has a peculiar sense of humor, and nowhere is this more apparent than in the rogues gallery of interstellar visitors. In less than a decade, we've hosted 3 confirmed guests from other star systems, each one arriving with a personality so distinct they seem designed to confound us. First came one Oumuamua in 2017, the cosmic equivalent of a stone-faced stranger walking into a small-town bar. No visible coma, no tail, no outgassing that telescopes could detect. Just a tumbling cigar-shaped object that reflected sunlight like polished metal. Its behavior was almost aggressively normal until it began accelerating away from the Sunday. The acceleration was small but measurable, about 10 micrometers per second squared. Yet it violated every expectation of how inert rocks should behave in space. The scientific community erupted in debate. Some proposed exotic mechanisms, hydrogen outgassing or radiation pressure on an unusual surface. The acceleration was real. Multiple observatories confirmed it, but its cause remained maddeningly elusive. Oumuamua had turned gravitational physics into a mystery novel. It left behind more questions than answers when it vanished. Then came Borisov in 2019, arriving like a familiar friend bearing exotic gifts. Here finally was an interstellar visitor that behaved like a proper comet. Bright coma, prominent tail, steady outgassing of water vapor and dust. All the features that astronomers expected from a chunk of primordial ice. But Borisov carried its own chemical surprise. An abundance of carbon monoxide that far exceeded anything seen in solar system comets. Its carbon monoxide to water ratio suggested formation in a colder environment than our own system. Now 3 Atlas has arrived as the third act in this interstellar drama, and its chemistry reads like a deliberate attempt to confound the patterns. Where Oumuamua showed no gas and Borisov showed elevated carbon monoxide, 3 Atlas dominates with carbon dioxide. The progression suggests a sampling of formation environments so diverse they might as well be from different universes. The morphological contrasts are equally striking. Oumuamua's elongated tumbling silhouette was extreme even by asteroid standards. Borisov, by contrast, appeared thoroughly conventional. A roughly spherical nucleus surrounded by a symmetric coma. 3 Atlas splits the difference in the most puzzling way possible. Its coma is compact and roughly spherical, but the subtle tail that finally emerged is strangely muted compared to Borisov's plume. The geometry suggests controlled, localized outgassing rather than explosive activity. The size estimates for each visitor tell their own story of diversity. Oumuamua was a cosmic needle. Borisov's nucleus was estimated at roughly half a kilometer across. 3 Atlas falls somewhere between these extremes. Each visitor samples a different scale of debris from the interstellar population. Perhaps most intriguingly, the 3 visitors arrived with completely different circumstances. Oumuamua was found when it was already racing away from the Sunday. Borisov was spotted while still approaching the outer solar system. 3 Atlas was caught at the sweet spot, far enough out to plan observations, close enough to begin detailed study immediately. The chemical signatures hint at formation in 3 distinct environments. Oumuamua's lack of outgassing might indicate processing by interstellar radiation. Borisov's carbon monoxide enhancement suggests birth in the cold outer reaches of a protoplanetary disk. 3 Atlas carbon dioxide dominance points to intermediate formation temperatures. The behavioral differences extend beyond chemistry to fundamental physics. Oumuamua's mysterious acceleration suggested forces beyond simple gravitational attraction. Borisov followed predictable comet physics with no unexplained deviations. 3 Atlas so far appears gravitationally well behaved, but its extended carbon dioxide coma challenges our understanding of how small nuclei generate such gas clouds. The observational bias effects are profound. What we see depends entirely on geometry, timing, and the sensitivity of our instruments. Oumuamua's lack of visible activity might have looked very different if WED caught it earlier. Borisov's textbook appearance might have seemed strange if WED observed it from a different angle. 3 Atlas' subtle tail might be far more dramatic when viewed from Mars perspective. Yet these 3 personalities already hint at the vast diversity waiting to be discovered. If the first 3 interstellar visitors are this different, what will the next dozen reveal? Each visitor is like a core sample from a different planet formation environment. The progression from Oumuamua to Borisov to 3 Atlas reads like the universe is challenging us. Just when we thought we understood the category, along comes another visitor to rewrite the rules. As 3 Atlas approaches its date with solar conjunction, we're left to wonder, is its strange personality the tip of an even stranger iceberg? Or are we simply learning that the space between the stars is far more diverse than we ever imagined? The dynamics puzzles. The universe has a way of hiding its most important secrets in the smallest deviations. And nowhere is this more apparent than in the subtle dance of forces that govern interstellar visitors. The story of 3 Atlas is at its core a story about physics in motion, about tiny accelerations that could reveal profound truths about matter between the stars. Oumuamua established the template for interstellar mystery. It began accelerating away from the Sun in a manner that defied gravitational models. The effect was tiny, about 1/100,000th of Earth's surface gravity, but it was persistent and measurable across weeks of observation. Multiple observatories confirmed the acceleration's reality. This transformed a straightforward gravitational problem into a puzzle that continues to generate research. The acceleration wasn't random. It followed a specific pattern that suggested outgassing from the Sun-facing hemisphere. But here's where Oumuamua became truly confounding. No telescope could detect the gas or dust that should accompany such outgassing. The object was accelerating like a comet, but looking like an asteroid. This created a contradiction that forced astronomers to consider increasingly exotic explanations. Some researchers proposed that Oumuamua might be outgassing hydrogen, a gas so tenuous it could explain the acceleration without creating a visible coma. Others suggested that radiation pressure on an unusually reflective surface could account for the motion. The most speculative hypotheses involved artificial origins. 3 Atlas, by contrast, has so far shown no comparable acceleration anomaly. Its trajectory matches gravitational predictions within observational uncertainty. But this apparent normalcy might be misleading. The non-gravitational forces that affected Oumuamua became apparent only during extended observation. 3 Atlas is still approaching perihelion, and the most telling measurements may come during and after its closest solar approach. The chemistry of 3 Atlas suggests that if non-gravitational forces do emerge, they might follow a different pattern. Carbon dioxide sublimation produces much more massive molecules than hydrogen. This creates a momentum transfer that's easier to detect but operates through different physics. If 3 Atlas begins showing measurable acceleration, it could provide the key to understanding whether Oumuamua's behavior was unique or a common feature. The viewing geometry adds layers of complexity to any dynamical analysis. Anti-solar tails can appear compressed or even invisible, depending on our line of sight. The Sun-facing coma elongation that Hubble detected in 3 Atlas initially puzzled observers, but 3-dimensional gas dynamics can create optical illusions. The extended carbon dioxide coma presents its own dynamical puzzle. How does a nucleus only a few kilometers across maintain such an active emission region? The physics demands either an extraordinarily active surface or a different mechanism. One possibility is that 3 Atlas is actually a loose aggregate of smaller fragments, each one outgassing independently to create the extended emission region. But if this were the case, we might expect to see evidence of fragmentation in the images. So far, Hubble's high-resolution imaging shows no such features. Another explanation involves the interaction between outgassing and the solar wind. As carbon dioxide molecules escape, they can be ionized by solar radiation. These electromagnetic forces could accelerate the gas to much higher velocities. This could potentially explain the enormous extent of the carbon dioxide cloud. The rotation state of 3 Atlas remains unknown, but it could hold crucial clues. Most small bodies tumble chaotically due to outgassing torques. If 3 Atlas is outgassing as vigorously as its coma suggests, it should be experiencing torques that would show up as brightness variations in long-term photometry. Yet, the photometric record shows remarkable stability. This could mean the object is spinning very slowly or is viewed nearly pole-on. Each possibility carries different implications for the object's structure and origin. The TESS observations have hinted at possible activity even at large distances. If confirmed, this would suggest the visitor was already active when it was farther than Jupiter. This implies either an unusually volatile composition or a different triggering mechanism. As 3 Atlas approaches perihelion, the dynamical questions will only intensify. Will it show the mysterious acceleration that characterized Oumuamua? Will its coma morphology reveal the jet structures that would explain its extended gas cloud? The answers could redefine our understanding of how interstellar matter behaves. The physics is playing out in real time, written in the language of orbital mechanics. We're watching dynamics that began in another star system millions of years ago, finally reaching their climax in the warm embrace of our sun's gravity. The global watch, who's observing what when? The astronomical community has transformed 3 Atlas into the most intensively monitored visitor in history. They have orchestrated a global observation campaign, a symphony of science. Every major space agency and ground-based observatory has joined the effort. NASA's Science Mission Directorate established the coordination framework, organizing a multi-mission approach that leverages every available asset. The Hubble Space Telescope provides the highest resolution imaging. The James Webb Space Telescope delivers infrared spectroscopy with incredible sensitivity. The Swift Observatory monitors ultraviolet emissions that reveal photochemical processes. The SPHEREX mission has emerged as an unexpected hero in this campaign. Originally designed for cosmological studies, its wide-field capability proved perfect for tracing the enormous carbon dioxide cloud surrounding 3 Atlas. The synergy between Webb and SPHEREX has created a complete picture. A picture no single instrument could have provided alone. Ground-based observatories worldwide have coordinated their efforts. The Gemini North Telescope in Hawaii captured the initial images of the compact coma. Its twin Gemini South in Chile provided the deep imaging that confirmed the tale. The Palomar Observatory's Zwicky Transient Facility contributes ongoing photometry, but the observational timeline is dominated by an unavoidable fact: solar conjunction. As 3 Atlas approaches perihelion, Earth's position creates a frustrating geometry. Just as this visitor reaches its most active phase, it will disappear behind our star's glare. It will be invisible to every Earth-based instrument for nearly 2 months. This blackout period represents one of astronomy's most maddening coincidences. The time when solar heating should drive 3 Atlas to its maximum activity will be unobservable. We'll miss the crescendo of this cosmic performance. We are left to study only the overture and the aftermath. The reappearance in early December will mark the beginning of the final act. 3 Atlas will emerge in the pre-dawn sky, positioned in the constellation Virgo. By then, it will be racing away from the sun at incredible speeds. It will grow fainter each night as it returns to the interstellar medium. The post-perihelion observations will be a race against time and distance. Signal strength will decline exponentially as the visitor recedes. Yet, this challenging timeline has inspired creative solutions. The Mars Reconnaissance Orbiter's high-rise camera represents a unique opportunity. An opportunity to observe 3 Atlas from an alien perspective. On October 3rd, the visitor will pass within 29 million kilometers of Mars. This could potentially allow orbital assets to capture images during Earth's blackout. The resolution wouldn't rival Hubble's clarity, but it would provide crucial data during a critical period. Several spacecraft currently traveling through the outer solar system are potential contributors. NASA's Psyche mission will pass within a reasonable distance on September 4th. The European Space Agency's JUICE spacecraft could attempt long-range observations in November. Even the OSIRIS-APEX mission has been considered for possible imaging. The coordination extends beyond traditional astronomical assets. Radio telescopes worldwide are monitoring for any electromagnetic emissions. Planetary radar systems are attempting to bounce signals off the nucleus. Even amateur astronomy networks have been mobilized to contribute photometric observations. The international cooperation has produced observation scheduling that resembles military logistics. Time allocation committees at major observatories have granted emergency observing slots. Data sharing agreements ensure that observations can be immediately correlated. This creates scientific synergies that multiply the value of each observation. The European Space Agency's Planetary Defense Office has coordinated tracking efforts. While 3 Atlas poses no threat, the techniques being developed will be invaluable. They will be invaluable for future planetary defense scenarios. As the observational window narrows, the intensity of global monitoring has reached a fever pitch. Telescope time that typically requires years of proposals is being allocated on weekly schedules. Data analysis that usually takes months is being compressed into days. The astronomical community has essentially declared 3 Atlas a cosmic emergency, not because it poses any danger, but because it represents an opportunity that will never come again. The December reappearance will test every aspect of this global coordination. The next few months will determine whether this unprecedented campaign yields breakthrough insights that could redefine our understanding of interstellar space. Could we fly to it? The romantic notion of chasing down an interstellar visitor crashes hard against reality. The unforgiving mathematics of orbital mechanics and the cruel realities of rocket science. Yet, the very impossibility of intercepting 3 Atlas has inspired creative mission design studies, proposals that push the boundaries of what's theoretically possible. The fundamental problem is time and velocity. 3 Atlas was discovered when it was already racing toward the inner solar system. Any intercept mission would need to match not just this enormous velocity, but also its precise vector. The energy requirements for such a trajectory place it firmly in the realm of science fiction. A dedicated interceptor mission would require delta-v measurements that exceed our capabilities. Even if we could generate the thrust, the travel time would stretch into years, by which time 3 Atlas would be long gone. But impossibility has never stopped aerospace engineers from dreaming. Several research groups have explored what might be achievable using spacecraft already in motion. The Psyche mission will pass within 0.3 astronomical units of 3 Atlas. While Psyche wasn't designed for comet encounters, it could gather valuable data. The JUICE mission, the European Space Agency's Jupiter Explorer, presents another opportunity. JUICE's trajectory will carry it within observation range of 3 Atlas on November 4th. This is during the period when Earth-based telescopes are blinded by the sunday. Its advanced instruments could provide crucial data during this observational gap. Perhaps the most audacious proposal involves NASA's Juno spacecraft currently orbiting Jupiter. A research team has calculated that a carefully timed trajectory modification could redirect it toward a March 2026 encounter with 3 Atlas. The plan would use Jupiter's massive gravity field as a cosmic slingshot, adding velocity through an Oberth maneuver that leverages the spacecraft's proximity. The Juno intercept proposal reads like space mission fantasy made manifest. The spacecraft would need to execute a precisely timed burn, while deep in Jupiter's gravity well. The timing would be critical. Miss the window by hours and the encounter becomes impossible. Execute the maneuver perfectly, and Juno could become humanity's first probe to fly by an interstellar visitor. But such proposals remain firmly in the analysis stage. Juno's current mission is scheduled to end in 2025. Any modification would require approval from NASA, extensive planning and oversight. The spacecraft's aging systems and limited fuel add additional constraints. The Mars encounter on October 3rd offers perhaps the most realistic opportunity. As 3 Atlas passes within 29 million kilometers, the MRO's high-rise camera could get images. While this wouldn't rival Hubble's clarity, it would provide a unique perspective. The OSIRIS-APEX mission has also been mentioned as a potential contributor. The spacecraft's instruments could provide unprecedented detail about the visitor's properties. However, the mission timeline and trajectory constraints make such observations speculative. Looking toward the future, the ESA's Comet Interceptor mission represents our best hope. Scheduled for launch in 2029, it is designed as a rapid response mission. It can redirect toward targets of opportunity, including newly discovered interstellar objects. The spacecraft will wait in a stable orbit, ready to launch toward whatever visitor arrives next. The academic literature on interstellar intercept missions has exploded since Oumuamua's discovery. These studies serve as feasibility assessments for future opportunities. They establish the technological and logistical requirements for missions that don't yet exist. The energy requirements for interstellar intercepts reveal just how different these visitors are. A mission to Mars requires a delta V of roughly 6 kilometers per second. A Jupiter flyby needs about 12. Intercepting an object like 3 Atlas would demand delta V values approaching 50 or more. That's beyond the capability of chemical rockets. It would require nuclear propulsion, solar sails, or theoretical technologies. Yet the scientific payoff from a successful intercept would be transformational. Close-range measurements could reveal isotopic ratios that encode its stellar environment, surface compositions that preserve the chemical conditions of alien planetary disks, structural properties that indicate how small bodies survive the journey. Such data would be worth decades of ground-based observations. The cruel irony is that each interstellar visitor is a laboratory sample delivered to our doorstep, yet moving too fast for us to properly collect it. We're like researchers watching valuable specimens parade past our laboratory window, tantalizingly close yet impossible to capture with current technology. As 3 Atlas continues its hyperbolic journey, the intercept studies serve as reminders of our current limitations and inspiring blueprints for future possibilities. We may not be able to chase this visitor, but we're learning how to be ready for the next one. Why carbon dioxide? Natural explanations on the table. The cosmic chemistry of 3 Atlas reads like a recipe from an alien cookbook, dominated by carbon dioxide in proportions that challenge every model we've developed. Yet before we venture into exotic explanations, the laws of physics offer several natural pathways that could produce such an unusual chemical signature. The carbon dioxide snow line hypothesis provides perhaps the most elegant explanation. In any protoplanetary disk, different volatiles condense at different distances from the star. This creates chemical zones as distinct as climate belts on Earth. Water ice dominates the cold outer regions, but carbon dioxide has its own freezing point. An object forming just inside the water snow line would incorporate abundant CO2 ice, while remaining relatively water-poor. This scenario places 3 Atlas berth in a region roughly analogous to our asteroid belt, warm enough that water existed as vapor, but cold enough for carbon dioxide to freeze. Such an environment would produce exactly the chemistry we observe, but stellar environments vary dramatically from system to system. Stars with different masses and luminosities create different temperature profiles in their disks. A low-mass star might push the carbon dioxide snow line much closer to the star, creating a larger zone where carbon dioxide ice dominates over water. Radiation processing offers another compelling explanation for 3 Atlas' strange chemistry. During its millions of years wandering interstellar space, this visitor has been exposed to radiation. high-energy particles can break apart molecular bonds and rearrange chemical structures. Such processing could explain both the carbon dioxide dominance and the apparent water deficiency. Cosmic rays might preferentially destroy water ice while leaving carbon dioxide relatively intact. The reddish coloration that spherics detected is consistent with radiation processing. The insulating crust hypothesis addresses one of the most puzzling aspects of its behavior. Why does it show such strong carbon dioxide emission while water signatures remain weak? Laboratory studies reveal that organic-rich mantles can form on icy surfaces, creating insulating layers that suppress volatile sublimation. If 3 Atlas developed such a crust, water ice might be abundant beneath the surface, but it would be prevented from reaching the gas phase by the overlying material. Carbon dioxide, being more volatile, could escape through cracks in this insulating layer. This would explain why Webb detects abundant CO2 gas while Spheric sees evidence for water ice. The water is there, but it's trapped below a surface layer. The icy fragments hypothesis suggests an entirely different mechanism. Rather than a single solid nucleus, 3 Atlas might be a collection of CO2-rich ice chunks. As solar heating intensifies, these fragments could separate and sublimate independently. This would create the enormous carbon dioxide coma through distributed outgassing. This fragmentation model would explain several puzzling observations simultaneously: the extended gas cloud, the stable brightness, and the subtle tail morphology. If 3 Atlas is essentially a flying gravel pile of carbon dioxide ice, its behavior would be unique. Temperature dependence provides yet another piece of the puzzle. At 3 Atlas, current distance water ice sublimation is relatively inefficient. While carbon dioxide remains highly volatile, the thermodynamics naturally favor carbon dioxide outgassing over water vapor production. As 3 Atlas continues warming, this temperature dependence offers a testable prediction. If the CO2 dominance is from thermodynamic effects, post-perihelion observations should show increased water. The carbon dioxide to water ratio should evolve in predictable ways. The grain size effects in the coma and tail provide additional clues. The subtle anti-solar tail suggests either unusually large dust particles or a unique composition. Laboratory studies of carbon dioxide ice sublimation show it can produce different dust aggregates. This could potentially explain the unusual tail morphology. Each natural explanation opens windows into the physics of planetary formation. Whether formed near a carbon dioxide snowline, processed by radiation, or representing fragments, this visitor carries information about stellar disk conditions that expand our understanding. The natural pathways are numerous, testable, and grounded in well-understood physics. Yet their very abundance creates its own puzzle. With so many plausible explanations available, how do we determine which one is the truth? Where could it have come from? Tracing 3 Atlas back to its stellar birthplace is like solving a cosmic murder case. The crime scene is light years away, and the evidence is encoded in orbital mechanics. Yet hidden within the visitor's trajectory are kinematic clues that point toward a specific origin. The thick disk hypothesis has emerged as the leading contender. Our Milky Way galaxy consists of several distinct stellar populations. The thin disk, where our Sun resides, containing relatively young metal-rich stars. The thick disk populated by older stars that formed when the galaxy was younger. And the ancient stellar halo containing the galaxy's oldest stars. Each population moves through space with characteristic velocities and orbital patterns. The velocity vector of 3 Atlas suggests membership in the thick disk population. These stars formed roughly 8 to 12 billion years ago, during what cosmologists call the epoch of cosmic noon. If 3 Atlas originated in this stellar environment, it is ancient. It represents material that has been wandering the galaxy since before Earth existed. The thick disk origin carries profound implications for understanding planetary formation. Stars in this population formed from gas clouds with lower abundances of heavy elements. The reduced metallicity would have affected the composition of any protoplanetary disks, potentially favoring carbon-bearing volatiles in ways that could explain free atlas chemistry. But the origin story extends beyond simple stellar demographics. It includes the violent processes that eject material from planetary systems. Gravitational interactions with giant planets can scatter smaller bodies onto hyperbolic trajectories. Close stellar flybys can similarly disrupt planetary systems, stripping away outer disk material. The ejection mechanisms create a natural selection effect in the interstellar medium. Only objects with specific sizes, compositions, and structures can survive the journey. 3 Atlas represents a survivor of this cosmic winnowing process. Population studies based on the 3 confirmed interstellar visitors reveal a sampling bias. This complicates any attempt to infer origin stories. We've detected one object with no visible outgassing, one with carbon monoxide enhancement, and one with carbon dioxide dominance. This might represent the true diversity of interstellar debris, or it might reflect the particular detection biases of our current survey systems. The galactic context adds another layer of uncertainty to origin stories. 3 Atlas has been traveling through space for millions of years, during which time it has experienced gravitational perturbations from every star system it has passed. These encounters have gradually modified its trajectory, erasing the kinematic fingerprints that would allow precise backtracing. We can identify the general stellar population it likely came from, but pinpointing the specific star system may be impossible with current data. The chemical clues provide more specific constraints on the formation environment. The carbon dioxide dominance requires temperatures and pressures that exist only in particular zones. If 3 Atlas condense from the gas phase, the thermodynamic conditions must have favored CO2. This suggests either unusual disk chemistry or formation at a specific orbital distance. Isotopic ratios could provide the smoking gun evidence for 3 Atlas origin, but measuring isotopes in such a faint, distant object pushes current techniques to their limits. Different stellar environments produce different isotopic signatures in their planets and debris. This creates chemical fingerprints that could identify not just the type of star system, but potentially the specific stellar mass, age, and metallicity of its parent star. The Rubin Observatory's survey promises to transform origin studies. From anecdotal case studies into statistical science, it will have the capability to detect dozens of interstellar visitors per year. Rubin will build a sample large enough to reveal population trends and chemical patterns. Early claims in some media outlets about an extragalactic origin appear unfounded. The kinematic evidence points firmly toward a Milky Way origin, most likely from the thick disk population. While the galaxy is vast, it's not infinite. The orbital mechanics place clear constraints on how far 3 Atlas could have traveled. The timing of 3 Atlas' arrival in our solar system might be pure coincidence, or it might reflect deeper patterns in galactic dynamics we don't yet understand. If the thick disk origin is correct, then 3 Atlas represents ejected material from billions of years ago. As we study this visitor's chemistry and dynamics, we're conducting archaeology on galactic scales. We are inferring the properties of ancient planetary formation environments from their debris. 3 Atlas is a time capsule, but one that has been tumbling through space for so long that its contents have been altered. The December observations will provide crucial tests of the origin hypothesis. If the post-perihelion chemistry shows predictable evolution, it will support conventional models. If the chemistry remains stubbornly anomalous, it might indicate processes beyond our current framework. The Avi Loeb chapter, open-minded and controversial. In the landscape of modern astronomy, Few figures generate more passionate debate than Avi Loeb, the Harvard astrophysicist whose willingness to entertain unconventional hypotheses has made him a controversial figure. His analysis of 3 Atlas exemplifies this complex legacy, meticulous in its observational foundation, yet bold in its theoretical implications. Loeb's engagement with 3 Atlas began almost immediately after discovery, manifesting in a series of detailed essays that tracked the visitor's evolving signature. His August 27th analysis proved particularly prescient. It claimed to detect the faint anti-solar tail that conventional observations had missed. Within days, the astronomer's telegram confirmed exactly what Loeb had predicted. But Loeb's interpretation of 3 Atlas extends far beyond confirming conventional features. His size estimates suggest a nucleus potentially tens of kilometers across, dramatically larger than Hubble's upper limit of 5.6 kilometers. This discrepancy isn't merely academic. It implies fundamentally different physics governing how this object interacts with sunlight. Either Loeb's brightness models are incorrect, or 3 Atlas has optical properties unlike any known object. The spheric spectral mapping data provides the foundation for some of Loeb's most striking claims. The vast carbon dioxide coma represents a scale of activity that challenges conventional models. Loeb emphasizes that such extensive gas production requires either extraordinary activity levels or new mechanisms. His interpretation of the water detection controversy illustrates his methodical approach. Early swift observations suggested significant water vapor, but SpherX found very little. Rather than dismissing either result, Loeb synthesizes them into a coherent narrative. 3 Atlas might contain water ice in its interior, but surface processes are preventing sublimation. Where Loeb's analysis becomes genuinely controversial is in his exploration of technological hypotheses. Drawing on the precedent of Oumuamua's unexplained acceleration, he examines whether conventional physics can explain it. His calculations suggest that purely natural outgassing might struggle to explain the enormous gas cloud. This leads him to consider whether additional energy sources could be contributing. The self-luminosity hypothesis is perhaps Loeb's most provocative suggestion. If 3 Atlas possesses internal energy sources beyond simple solar heating, it could maintain high activity. Such internal energy could power the extended carbon dioxide production, while remaining undetectable through conventional astronomical observations. Loeb's trajectory analysis adds another layer of intrigue to his hypothesis. He notes that 3 Atlas path displays geometric properties that optimize observation from Earth, almost as if the trajectory were designed for maximum scientific impact. While this could be chance, Loeb argues, we should at least consider intentional navigation. The intercept mission proposals that Loeb has co-authored are his most concrete contribution. Working with spacecraft trajectory specialists, he has outlined detailed scenarios for redirecting Juno. These proposals include specific burn timing delta-V requirements and instrument capabilities. Yet even Loeb acknowledges the speculative nature of his more exotic hypotheses. His essays consistently frame technological explanations as alternatives to be tested, not as conclusions to be accepted. The scientific method demands that we consider all possibilities consistent with the data. The media response to Loeb's analysis has followed predictable patterns. Headlines about possibly hostile technology distort his carefully qualified speculations. Such coverage misrepresents both Loeb's actual arguments and the scientific process. Loeb proposes technological scenarios not because he believes them to be true, but because they represent testable alternatives to conventional explanations. His approach exemplifies a broader philosophy about how science should engage with anomalous data. Rather than forcing observations into existing theoretical frameworks, Loeb advocates for expanding them. This methodology has historical precedent. Many breakthrough discoveries in astronomy began with observations that didn't fit. The testing protocols that Loeb outlines provide a roadmap for resolving the mystery. High-cadence photometry could reveal whether the object's brightness varies artificially. Spectroscopic monitoring could detect emission lines that indicate exotic chemical processes. Close-range spacecraft encounters could measure properties impossible to determine from a distance. Loeb's collaboration with mainstream observational teams demonstrates his commitment to evidence. His size estimates and chemical interpretations are grounded in the same data as other researchers, though his willingness to explore unconventional explanations often leads to different conclusions. The scientific debate about 3 Atlas has been enriched by this diversity of perspectives. The temporal pressure surrounding observations adds urgency to Loeb's arguments. With only months remaining before the visitor disappears, the window for gathering evidence is closing. If technological hypotheses are to be tested, the tests must happen now. As the solar conjunction approaches, Loeb's analysis serves as both a scientific and philosophical statement. His willingness to consider possibilities that other researchers avoid reflects a broader question. How should science respond to genuinely anomalous data? The 3 Atlas controversy may ultimately be remembered not for the specific hypotheses it generated, but for the scientific methodology it exemplified. The careful balance between healthy skepticism and genuine open-mindedness, what could confirm or falsify theories. Next, the approaching solar conjunction of 3 Atlas creates a natural experiment in astronomical patience. But the December reappearance will trigger one of the most intensive observational campaigns in history. The tests that await our interstellar visitor represent a scientific trial by fire, where competing hypotheses about its nature will face the ultimate jury: observational reality. The post-perihelion spectroscopy holds the key to resolving the chemistry mysteries. If natural sublimation physics governs this visitor's behavior, the CO2 to water ratio should evolve. The nucleus temperature will have peaked during the unobservable perihelion passage, potentially breaking through any insulating surface layers that suppressed water vapor. December and January spectra should show increased water emission if this is the case. Conversely, if the carbon dioxide dominance persists unchanged through perihelion, it would suggest a genuinely water-poor composition. Such persistence would challenge conventional models of cometary volatile evolution. High-cadence light curve observations represent another crucial test. If 3 Atlas is a conventional nucleus, its brightness should show predictable patterns related to rotation state and jet activity. Most active comets display brightness variations on time scales of hours to days. The absence of such variations would suggest unusual uniformity or a specific viewing geometry. More dramatically, any evidence of artificial illumination would show up as unusual variations. Such signatures would be extraordinarily difficult to fake through natural processes. The photometric monitoring will essentially place 3 Atlas under continuous surveillance. Resolved imaging campaigns will trace the evolution of coma morphology. Natural outgassing models predict specific patterns of dust release and tail development. The shape, orientation, and growth rate of any tail structures will provide detailed tests. The Mars-adjacent observations on October 3rd represent a unique opportunity, an opportunity to study 3 Atlas from an alien perspective during Earth's blackout. If the Mars Reconnaissance Orbiter can capture images, the data would be crucial. The viewing geometry from Mars will be completely different from Earth's perspective, potentially revealing asymmetries or directional effects that are invisible from our vantage point. Opportunistic spacecraft observations could provide the most definitive tests of 3 Atlas nature. The Psyche mission's September encounter or JUICE November observations offer possibilities. Spacecraft data could resolve the nucleus directly and measure magnetic field interactions. The James Webb Space Telescope's follow-up observations will push infrared spectroscopy to new limits. Webb's ability to detect trace organic compounds and measure isotopic ratios could be key. If 3 Atlas shows isotopic signatures characteristic of the early galaxy, it would support the thick disk origin. Anomalous isotope ratios might indicate processing by exotic mechanisms. Spheric's continued mapping of the carbon dioxide cloud will test its evolution. Natural outgassing models predict specific relationships between distance and coma size. Perhaps most importantly, any detection of non-gravitational acceleration would be crucial. The precision astrometry needed to detect such effects requires months of continuous tracking. If acceleration anomalies emerge, their magnitude and direction could distinguish between different causes. The synthesis of multiple observational approaches will converge on conclusions. Natural explanations for 3 Atlas behavior make specific testable predictions. Technological hypotheses predict different patterns of correlation. The December through March observation window represents humanity's final opportunity. After that, 3 Atlas will fade beyond the detection limits of even our most powerful telescopes. The observational tests that await our visitor represent both opportunity and responsibility. The chance to add another crucial data point to our understanding of the universe, and the obligation to pursue that understanding with rigor and open-mindedness. The universe has delivered 3 Atlas to our cosmic doorstep for reasons we may never fully understand. Our response to this gift will determine whether we emerge with expanded knowledge or expanded mystery. The bigger picture, preparing for the next one. The story of 3 Atlas extends far beyond a single interstellar visitor. It represents the opening chapter of a new era in astronomy, an era where the space between stars transforms from an empty void into a populated realm. As we struggle to understand this visitor, we're laying the groundwork for studying dozens more. The Rubin Observatory's legacy survey of space and time stands poised to revolutionize our understanding. Beginning full operations in 2025, Rubin's capabilities will dwarf current surveys. Theoretical estimates suggest this cosmic census could detect anywhere from 1 to 70 interstellar visitors per year. The transformation from anecdotal discoveries to statistical samples will fundamentally change the science. Instead of treating each object as a unique mystery, we'll begin to identify patterns. 3 Atlas, Oumuamua, and Borisov will serve as the calibration data set for this new approach. The European Space Agency's Comet Interceptor mission represents our most ambitious attempt to prepare. Scheduled for launch in 2029, this innovative spacecraft will wait in readiness. When the next interstellar visitor arrives, Comet Interceptor could redirect toward it within months. The mission design philosophy acknowledges the fundamental challenge of studying these visitors. We need to be ready before they arrive, not scrambling to respond after discovery. The spacecraft will carry a suite of instruments designed specifically for high-speed encounters. The rapid response framework being developed has applications that extend beyond pure science. The same survey systems that detect cosmic wanderers also monitor for potentially hazardous asteroids. This creates synergies between planetary defense and interstellar research. The techniques being refined for tracking 3 Atlas will prove invaluable for any future impact threats. The public engagement challenges surrounding these visitors require a careful balance, a balance between scientific honesty and responsible communication. Each new discovery triggers media speculation about alien origins. This creates opportunities for both education and misinformation. The 3 Atlas experience has demonstrated the importance of clear, immediate scientific communication. The data pipeline innovations developed for 3 Atlas set new standards for coordinated observations. The real-time integration of data from multiple telescopes has created unprecedented synergies. This collaborative framework provides a template for studying future interstellar visitors. The industrial and academic partnerships forged during this campaign, have established new models. The traditional astronomical culture of carefully planned observing programs has proven too slow. Instead, we've developed rapid response protocols that can redirect major facilities within days. The theoretical framework for understanding interstellar visitors has expanded dramatically. 3 Atlas has added carbon dioxide chemistry to this framework. This creates a more complete picture of the possible chemical environments where debris can form. Future visitors will test and refine this framework. The philosophical implications extend beyond astronomy into fundamental questions. Questions about the nature of planetary formation and the prevalence of life. If the chemical diversity we've observed in just 3 visitors reflects the true range, the galaxy harbors a vast library of different chemical recipes for building worlds. The technological development driven by this science has accelerated innovations in several fields. Improved spectrometer sensitivity, faster image processing algorithms, and more sophisticated software. These advances will enhance our capability to study all small body populations. The international cooperation that 3 Atlas has inspired provides a model for future challenges. When the universe delivers phenomena that require a rapid response, the community has demonstrated unity. This collaborative spirit will prove essential as we prepare for future encounters. The educational impact has already begun reshaping how we teach planetary science. Students now study examples from other star systems, not just our own. The chemical diversity revealed by these visitors provides concrete evidence that planetary environments can differ dramatically. As we prepare for the next interstellar visitor, the lessons learned extend beyond technical capabilities. They encompass the intellectual frameworks needed to interpret genuinely alien phenomena. The cosmic perspective that emerges from studying these visitors is both humbling and inspiring. We live in a galaxy where planetary debris regularly crosses the boundaries between star systems, creating a slow but steady exchange of material that connects distant worlds. 3 Atlas represents just one thread in this vast cosmic web, but studying it reveals the intricate patterns that bind our galaxy together. The universe keeps sending us these messengers from the deep, each one carrying news from regions of space and time that we can explore in no other way. Our response to these cosmic gifts will determine how well we understand our place. As we watch 3 Atlas disappear into the solar conjunction blackout, we're not just losing sight of one visitor, we're preparing for an era when such visitors become regular features of our astronomical landscape. When the space between stars transforms from mystery into familiar territory, the next messenger is already out there somewhere in the cosmic dark, following its own ancient trajectory toward our solar system. When it arrives, well, be ready. Thank you for spending this time with us tonight here on the Sleepy Explorer. If you enjoyed this journey, don't forget to subscribe so you can drift off with us again on the next adventure. For now, we wish you a peaceful night's rest. Good night, and thank you for tuning in.